Okay, so fundamental theorem of algebra and regression. In this section, we'll pull together several different ideas from this chapter and use them to analyze and graph polynomial functions.
Yeah.
Correct. First, a brief review of terminology. Again, they're revising it. Some summary: zeros, factors, solutions, and intercepts. So, if you have a polynomial equation, fx is equal to a n x raised to n,
Yeah.
correct, and so on with decreasing power of x, be a polynomial function. The following statements are equivalent. Solution: a zero, sorry, zero. K is zero of polynomial f. If k is a zero of polynomial f, means when I put k in place of x, I'll get my answer as zero.
Yeah, right. Yeah.
Your factor theorem. If k is a zero, then x minus k will be a factor. K is a solution of the root of the polynomial fx is equal to zero.
Yeah.
So the zero is for a polynomial. A solution is for the equation.
Equation, yeah. And factors for
Factor is x minus k.
Yeah,
X minus k. So that's the difference.
But they're all they're all the same thing.
Same thing, yeah, but it's used in a different context.
Yeah.
So like zero is for a polynomial.
Yeah.
Factor is when you put in x minus k in bracket.
You wouldn't say factor, find a factor for this graph. Like
yeah. You won't say that. Yeah. Solution root is for the equation.
Yeah.
X-intercept, if k is a real number, k is an x-intercept of the graph. If the graph passes through k comma 0. Yeah. Obviously, you put y is equal to 0, you get the value of x. Yeah. To start with, please type this on the Desmos. You know what happens on it? So what changes when B and C changes? You come to know the different shape of the graph.
Yeah, like when it would go like
up, both will go up, one will go up, one will go down, and all that thing will keep on happening. Now close your laptop. Now try to match the function with the graph. So which one will this be?
This one was B because of so since it's an even power, it's only bouncing on the x-axis.
And what do we call this? Which are my repeated roots? 3 and minus 2.
3 and minus 2
are the repeated
roots. And but it bounces.
So bounces is a repeated root.
Yeah. When it bounces,
when it bounces, it's called repeated root. It's changing and it's giving you the two same answers.
Yeah.
So yeah. The next one.
2 is A.
2 is A because very clearly,
Yeah. It's because odd roots.
And 3?
And 3 is obviously C.
Now see, this is very important. When it's a cubic, this will be the point of inflection. Cubic will have a point of inflection. So when you have linear, see, like these are all linear. Linear, like x minus a is a linear.
Yeah.
So linear will cut the x-axis. Like see, this is linear.
Yeah.
So the graph will cut at minus 2. See, it's cutting. Linear will cut. Quadratic. If you have x minus b square, what will it do?
X minus b squared.
It will bounce.
Bounce.
Bounce or touch the x-axis. So it will basically bounce. If it's a quadratic.
Yeah.
And if it's cubic, if it's a cubic factor, then what will happen?
Then it will not bounce, it will go straight through.
Yeah, point of inflection. It will become straight and then it will go up.
Yeah.
That's called a point of inflection. Three things
that should run. Yeah.
3 things, main things. They'll ask you to reverse graph this. So you have to learn this up. Yeah, see.
Oh, like this.
Use what you know about the intercepts in the end behavior. Use synthetic substitution to find a few additional values to make your graph more accurate.
Synthetic substitution is plugging in any number. Right?
Yeah. Now, first thing is what will you do?
First thing?
It's a cubic graph.
So you put the x.
You can see cubic graph?
Yeah, because
x and x squared. Yeah. So cubic graph is how? Like this.
Yeah.
Correct?
Yeah.
But it's a negative, but the leading coefficient is negative. So first you think of this, second you think of this. Leading coefficient is negative. Means it will get reflected.
Yeah.
And how does this graph become? Go on.
So if it's going from, if it's like this originally, it would go like this.
Like this.
Yeah.
Okay.
So negative is like, I need to remember these things.
Yeah, you have to remember this. It's important. Therefore, you watch this video several times. If you want to watch this video seven
times down.
Okay. So this is linear.
Yeah.
So the graph will cut
at -2.
At x is equal to -2. This is a quadratic.
So it bounces.
Bounce, or it will touch the x-axis. That's what we use. Touch the x-axis at
-1.
At x is equal to 1. Correct? So if you have 0, you want to keep 1 here, like this. 1, 2, correct?
Yeah.
3, -1, -2, -3.
Yeah.
Right? This is 1. I hope this would give me a good graph. It is not well extended.
Yeah.
Now, take some values.
So x of 0.
Synthetic substitution is not required. Actually, you can directly do direct substitution because they are already the factors. So if you take x is 0, 0 plus 2, correct? 0 minus 1 square. Yeah, but it's easier to do this way. You already have the factors. So minus 2, correct?
Yeah.
Into minus 1 square is 1. So basically minus 2.
2.
So 0 minus 2. Okay, we are getting 0.
So that's already 3 points. That's all you need.
Yeah. Okay, we got 0 minus 2. Then
you can draw it.
1 we know. 1 is touching it.
Yeah, 1, yeah, and then -2.
And minus 2 is 0.
And it's cutting through.
It's cutting through. So that means your graph would something be like this, and it bounces off like this. Check using your calculator. You can take x as 2, x as minus.
He said all you need is 3 points. Any graph, all you need is 3 points.
3 points user, it's fine. If you then you have to get the coordinates of the turning point. Now, what is turning point? Another important characteristic of a polynomial graph function is that they have turning points.
Yeah.
They have turning points corresponding to local maximum and local minimum. So this is your local minimum probably, and this is your local maximum.
Right.
Y coordinate of a turning point is a local maximum, and y coordinate of a turning point is local minimum. If it's a maximum, then it's higher than the other nearby points.
Obviously, yeah.
Local minimum is lower than the other nearby points. Therefore, it's called local minimum, local maximum.
Yeah.
Because it's nearby.
Yeah, nearby, but not the main minimum.
And like you stand first in your class, in your school.
The local maximum.
No, local. You're a local scholar.
Local maximum.
Local scholar. But when you appear for IB, you're ranking way. Because you're a local hero.
Local, yeah.
Turning points, zeros of polynomial functions. A graph of every polynomial of degree n has at most n minus 1 turning points. And at most n zeros. So your degree n, if you have, so how many turning points will it have? It will have one less turning point than the degree.
Yeah.
N minus 1.
N minus 1.
At most,
At most.
It can be lesser than that, but at most, like if it's a quartic equation, raised to 4.
Yeah.
How many maximum turning points it can have?
4.
3.
Oh, sorry, not 3 because
1 less.
1 less.
Okay.
Every time 1 less. So if it's 5, there'd be 4. If there's 20,
at most 4.
At most 4. If
so it can have 2 also. You can have 3 also. But at most 4.
At most, so if it's
Max.
20, it would have maximum 19.
Yeah.
Right. Okay.
Those are the turning points. And zeros? How many zeros at the most? At most, how many zeros will it have? N.
So all. So like if it's 5, then 5.
5.
So the 5.
At most 5.
Maximum 5.
5. Because the repeated root comes in, then it will be less.
Yeah.
You saw that something?
Yeah.
They were repeated roots, so minus 1, 2, and the other 2 were there.
The other sheet. No?
Other sheet, yeah. Are you understanding this?
Yes.
Consider the function fx is equal to x raised to 4 plus 4x cube plus 3x square minus 4x minus 4. Use your graphing calculator to identify the x-intercept. So let's do that. Use your graphing calculator.
What's that 1? Minus 2,
4,
1 and 1.
Minus 2, 1 and 1. Repeat it.
Sorry, minus 2, minus 1 and 1. Sorry.
Okay. So none of them are repeated? This is repeated. The first one is touching it. Okay, no.
So yeah, minus 2 is repeated, right?
Minus 2 is repeated, no?
Because it's going up after. It's not going down though, it's going up.
So minus 2. Yeah, so minus 2 is repeated. This is repeated.
Oh, I thought it was only when it goes any change in direction.
Yeah, any bouncing. Any bouncing. It can bounce up, down, any bouncing. Any so that's touching it, no?
Yeah.
Correct?
Yeah.
Use a graphic calculator to find the x, y coordinate of the local maximum, local minimum. Chalo.
So
give you answer nearest 100.
Oh.
Nearest 100 means how many decimals?
Nearest 100. What?
2 decimals.
3 decimals.
2.
Tenths, hundreds,
thousands. Tenths, hundreds.
Uh-huh.
So after the decimal, tenth and then 100.
Okay.
There's no units.
So maximum 3.
Tell me the coordinates.
This is the relative maximum, correct?
Yeah. There's the first one is also there. No? The first one is minus 2, 0. That's the local minimum.
Oh yeah, right.
Correct?
No, isn't this the local minimum?
That is also local minimum.
No, this is the minimum. This is the local.
Both are local. There are 2 local minimums. This is minus 2, 0. Go over there. Achha, what's the local maximum?
Local maximum is minus 1.37.
Local maximum minus 1.37, comma
0.348.
0.348.
Yeah.
Achha, now tell me the local minimum. There will be 2 local minimums.
So the first one would be 2, 0.
Minus 2, 0.
Minus 2, 0. And then 0.366, minus 4.85.
Now sketch the graph. So what will you do?
So you would label the x-intercepts first.
One second. Should I? 3, 4, 1, 1, only. It's a very small graph here. 2, 3, 4, 5. Minus 1, 0. This is minus 2, minus 3, minus 4, minus 5, minus 6. Correct?
Yeah.
This
so
is 1, 2, 3, 4, 5, 6.
Yeah.
Minus 1, minus 2, minus 3, minus 4, minus 5, minus 6.
Yeah.
So this would be minus 2, 0. This is just bouncing of this, correct? It's like this. Huh?
Yeah.
Local minimum. This is 0.366 and minus 4.85 here. Correct?
Yeah.
What are my intercepts?
Minus 2, we should already have. Minus 1.
Minus 1, so it's cutting here.
And then 1.
And 1, it's cutting here like this. And what's your y-intercept?
Y-intercept?
Minus 4.
Minus 4.
Because you put a 0, minus 4.
Right.
It's cutting here. So you have to take care of all this. And you draw your graph. There's a local maximum here also, no? There'll be here also local maximum.
At the top.
Minus 1.37 here, no? Yeah.
Right.
And 0.3, yeah. We didn't mark that. It's a very squeezed up graph. But
you get the point.
You got the point. Okay. Write a polynomial model and find the maximum. Chalo.
You're making a rectangular box that is 16 by 20 inch piece of cardboard. The box will be followed in cuts to represent the volume of the box and find the dimensions which give the largest possible volume. So it's a box 16 by
You're cutting it off from
the inside corners.
Yeah, cutting off the corner. So what are you doing is you're cutting off the corners.
Yeah.
So these corners will be cut off.
Yeah.
This corner is cut off, this corner is cut off. So these corners have been cut off, right? These corners have been cut off.
Yeah.
Correct?
Yeah.
Huh? And you're making a rectangular box out of a 60-inch by
20 inches.
So this is 20 inches and this is 16 inches.
Yeah.
Correct?
Yeah.
And you're cutting this off, means this is x. You're cutting off this square of side x.
Yeah.
Find the dimensions of the box. Write down the equation that represents the volume of the box. So what is the length of the box?
The length would be 16.
When I say length of the box, I'm asking you, this would be the length of the box. You'll cut off these corners and
So
you'll fold this to form a box like
it'd
this.
be 20 minus 2x?
Yeah. So the length will be 20 minus 2x. Very good. What will the breadth be?
16 minus 2x?
Yeah, obviously.
Yeah.
Because see, from 16, you're cutting off the x from here and x from here.
Yeah.
So
but
this would be 16.
How would you get the width then? How would you find the width?
This is the length. Huh? So from the 20, you cut off x from here, x from here.
Ah, yeah.
Correct now?
Yeah.
You're cutting from both the sides. Huh?
Yeah.
And what will the height be?
The height would be
But you're folding this, no? So x, no? This will just fold up, no?
Which height? The
height of the box.
Height of the inside with the cutting of the edges. So x.
You're just folding it up.
Yeah, you're
no?
just folding it. Yeah.
Correct?
Yeah.
So what will the volume be therefore?
You multiply all three of these together. Times x. Yeah.
Right?
Yeah.
And find a dimension which gives the largest possible volume. So now you graph this.
Yeah.
So use GDC to graph v is equal to 20 minus 2x, 16 minus 2x and x. You graph it and find the max. View window, you could make it standard. Yeah, okay, then also you. If it doesn't come in that, then you'll have to zoom in properly.
Is this it?
How much is it?
181.
It can't be 181, no, because this is 20.
Yeah.
So view window, you must make it standard. View, make it standard.
Standard as in?
Window setting, yeah, it's there. Window 4, right?
Yeah.
Standard 5. Okay. Now you can zoom.
Yeah.
Can zoom in. Zoom or analyze graph will come later. First you need to zoom in properly.
Zoom out.
Zoom fit. If you can't see it, now zoom fit, you don't have to fit the graph. Yeah. Zoom fit, you don't have. Yeah. So zoom fit will go it.
So you go to maximum.
Menu 4, then zoom fit is the A, last one.
Okay.
So that will fit in everything. Now you analyze graph. Now you find max. Now you see this is 16. So it can't be more than 16, no?
Yeah.
No, now. Yes, sir. So 2.94. So 2.94. So x would be 2.94. And your maximum volume would be how much? 480?
420.
420, yeah. And the maximum volume is 420.
Nice. So that's for the maximum, for the largest possible volume.
Yeah. Because your graph, if you see, your graph will go like this, and like this. So this is your maximum meter.
Right.
So we'll stop here and we'll continue this next time, the regression.
Yeah. Online on Saturday.
Online on Saturday, yes.